A desert that drinks its own rain is not a fantasy but an ancient reality. Forgotten engineers mastered the art of turning solid rock into flowing water systems, and their secrets are more relevant today than ever before. By the end of this journey, you will understand how to pull water from stone using methods that defy our modern assumptions. We will explore how entire civilizations flourished in sand and sun, and uncover why their most brilliant water solutions were carved not from metal, but from the earth itself. What does it truly mean to build for a future without end? Sunlight pounds the earth into a fine, shimmering dust. In this world of endless sand and relentless heat, a single day without water is a crisis. Ancient peoples did not merely visit these deserts, they made them home, and their survival hinged on a single, desperate question. Where do you find drinkable water when the rivers are dry for years at a time, and the rain, when it comes, vanishes almost instantly into the thirsty ground? This was the fundamental challenge that shaped every aspect of life, from the vast expanse of the Sahara to the rocky plains of Arabia. Geography dictated destiny. Settlements did not spring up at random. They clung to the few natural oases, or, more importantly, they emerged wherever human ingenuity could create a new one. Archaeologists studying these sites often speak of a specific kind of resilience, a deep understanding of the land that modern observers can scarcely comprehend. The people living here did not see a barren wasteland. They saw a landscape full of hidden potential and subtle signs. They knew that the real water was not on the surface, but beneath it, locked away in underground reservoirs or fleeting desert storms. Their very existence depended on learning to catch that which fled and to store that which was scarce. This urgent, non-negotiable need is what sparked the first brilliant ideas. It forced a shift in thinking, from searching for water to knowing how to manufacture it from the environment itself. The story of how they began this process, of how they first convinced the desert to give up its most precious secret, starts with a simple, powerful observation about the nature of stone and rain. A desert traveler might walk for days and see nothing but sand and rock, until one day the ground simply opens up. A deep, dark shaft drops straight down into the earth, a silent mouth in the middle of nowhere. This is not a natural cave. Its walls are too straight, too perfect. It is the first clue to one of history's greatest water mysteries, the entrance to a qanat. For over 3,000 years, Persian engineers mastered this incredible technology, a subterranean river highway that defied the desert sun. These were not simple ditches. They were meticulously crafted tunnels, often stretching for miles, that tapped into secret water reserves trapped deep within mountain aquifers. The genius was in the slope. By carving the tunnel with a gentle, consistent decline, the water would flow effortlessly for vast distances, powered by nothing but gravity, arriving cool and clean at the surface without a single drop lost to evaporation. Ancient texts from the region speak of these qanats with profound respect, calling them the veins of the civilization, the reason cities could bloom in the sand. Building one was a monumental task. Workers began by digging a series of vertical shafts down to the water table, sometimes reaching depths of 200 feet. These shafts served as both access points and ventilation chimneys during the grueling construction. From the bottom of the mother well, teams would then carve a horizontal tunnel, inch by inch, back toward their destination. The tunnel walls were often lined with stone rings to prevent collapse, a testament to the builder's understanding of structural integrity. The result was a hidden network, a secret river flowing silently beneath the feet of the desert. In the city of Ghanabad in Iran, one of these ancient qanats is still in use today, delivering water to farms and homes just as it has for millennia. It is a stunning example of sustainable engineering, a system that requires no pumps, no external power, and leaves almost no footprint on the landscape. It makes you wonder, in an age of complex technology and energy-intensive solutions, what could we learn from this low-tech brilliance? How might we reapply such timeless principles to address our own modern water shortages? The Qanat was only the beginning, a masterclass in harvesting water from deep below. But other forgotten engineers looked not down but up, finding a way to catch the rain itself as it fell. High up in the mountain deserts, another kind of water harvest was taking place, one that pulled moisture not from the ground but directly from the air itself. In places like the Canary Islands, ancient engineers observed how morning fog clung to the leaves of certain trees, dripping steadily to the ground. They realized the dense fog was not just weather, it was a moving river of microscopic water droplets. Their solution was both simple and brilliant. They stretched vast nets of woven plant fibers across rock formations on windward slopes, turning entire hillsides into massive condensation surfaces. As the fog blew through these meshes, countless tiny droplets would collide with the fibers, stick to them, and merge until they grew heavy enough to drip down. Channels carved at the base of the nets would then guide this newly formed water into waiting jars or irrigation ditches. Ethnographers studying these sites note the incredible precision involved. The placement was everything. A net placed just a few feet too low might miss the densest part of the fog bank, while one placed too high could be torn apart by the wind. It was a perfect marriage of keen observation and practical engineering. The science is straightforward yet elegant. Fog is essentially a cloud touching the ground, filled with tiny, airborne water spheres. When these spheres are pushed by the wind against a mesh surface, they are captured. As more and more droplets collect, they coalesce into larger drops that gravity eventually pulls downward. The choice of material was critical. Ancient cultures used what was locally available, from resilient shrubs to carefully arranged stone walls that served the same function. Modern projects now use specialized polymer meshes that are even more efficient, but the fundamental principle remains unchanged. Perhaps the most striking example comes from the Atacama Desert in Peru, one of the driest places on Earth. Here, ancient communities used fog-catching techniques to sustain small-scale agriculture in an environment that receives virtually no rainfall. They were living proof that even an invisible water source could be made tangible and life-giving. It forces us to ask what other unseen resources surround us, waiting for the right kind of simple innovation to bring them into use. This ingenuity did not stop with capturing water from the air. Another group of forgotten engineers looked at the very rock beneath their feet and saw not an obstacle but the perfect storage container. A desert guide kneels, brushing sand from a stone slab that seems no different from any other. Then he pries it open, revealing a darkness beneath, a cool breath rising from a perfectly carved chamber hidden below the cliff face. This is a rock-cut cistern, one of thousands scattered across the ancient world, a secret kept by the stone itself. The Nabateans, the master builders of Petra, were not just carving temples and tombs, they were carving survival, transforming solid rock into immense, waterproof tanks that held the desert's most fleeting gift, the rain. Their genius lay in knowing which rocks could keep their water safe. Geologists today point to limestone and certain sandstones as the ideal candidates. These rocks are dense and have low porosity, meaning water cannot easily seep through their microscopic structure. the Nabatean engineers, through generations of observation, learned to identify these impermeable layers. They would find a massive, unbroken slab of such stone, and then, with astonishing patience, they would hollow it out, creating a vast, seamless bowl. The rock itself became the container, but creating the storage vessel was only half the battle. The other half was filling it. Across the cliff faces and pavements of their cities, they carved a spiderweb of subtle channels and gutters. These channels were designed to capture every drop of runoff from a rare desert downpour, directing the torrent away from the fragile structures and straight into the mouths of these hidden cisterns. The construction was a multi-stage marvel of hydraulic engineering. It began with a meticulous survey of the land, identifying natural catchment areas where water would naturally flow and gather. Then the arduous work of excavation started. Using iron chisels and stone hammers, workers would painstakingly carve out the main chamber, often giving it a bell-shaped profile to resist the immense pressure of the surrounding earth. Before the water was allowed to enter, the cistern was prepared. Layers of sand and gravel were often added at the inlet, acting as a natural filtration system to remove silt and debris, ensuring the stored water remained clean for months, even years. The scale of this ambition is breathtakingly illustrated by the Marib Dam in ancient Yemen. Here, a massive earthen dam captured seasonal floods, but its true power was unleashed by a network of secondary cisterns and distribution channels carved directly into the mountain rock. This system supported a civilization of hundreds of thousands in the heart of the Arabian desert, turning a barren landscape into a fertile kingdom for centuries. It was a testament to living in harmony with a harsh environment, not fighting against it. These cisterns were not just technology, they were a philosophy of patience and foresight, a deep understanding that security came from working with the materials the earth provided. This profound connection to the landscape would soon be tested by even grander projects, where the goal was not just to store water, but to command the flow of entire rivers. The desert floor may appear desolate, but beneath its surface lies a hidden ocean. Deep within the rock, vast aquifers hold water like a colossal sponge, treasures accumulated over thousands of years. Finding and tapping these secret reserves was the ultimate challenge for desert engineers, a quest that required not just strength, but a profound understanding of the Earth's hidden anatomy. One of the most remarkable feats was accomplished by the Garamontes of the Sahara. In a landscape we now see as empty, they built a flourishing civilization by accessing fossil water, ancient rainfall trapped in porous rock layers since a wetter climatic era. Their method was the Fagara, a system much like the Persian Qanat, where long, gently sloping tunnels were dug to intersect these water-bearing strata and guide the flow to the surface. The true genius, however, began long before the first shovel hit the ground. How do you find water you cannot see? Without satellites or ground-penetrating radar, these early hydrogeologists relied on a deep literacy of the land. They learned to read the subtle clues. A specific line of green vegetation snaking across an otherwise barren plain could hint at an underground fracture channeling water. The presence of certain water-loving plants, even in stunted forms, served as a living map pointing toward the moisture below. Once a promising site was identified, the arduous work of excavation began. Using primitive hand augers and stone tools, crews would drill down, sometimes for hundreds of feet, through layers of unyielding rock. The danger of a collapse was constant. To prevent this, they developed ingenious reinforcement techniques, lining the shafts with interlocking stone rings or baked clay cylinders that acted as a permanent casing, holding back the earth and ensuring the well's structural integrity for generations. This mastery is perfectly illustrated by the Aflaj systems of Oman. These ancient channels, fed by wells tapping into mountain aquifers, have been continuously maintained for over 2,500 years. They are not merely relics, they are living infrastructure, still delivering water to vast groves of date palms through a network governed by precise water-sharing schedules and community upkeep rituals. The water drawn from these depths was often exceptionally pure, filtered naturally through countless layers of sand and stone. Yet this very purity points to a profound modern dilemma. Fossil water is not a renewable resource in a human lifetime. The Garamontes, for all their brilliance, eventually saw their aquifers dwindle after centuries of extraction. This raises a critical question for us today. How do we balance the immense value of these ancient waters with the responsibility to use them sustainably? The answer, perhaps, lies not just in drawing water out, but in finding smarter ways to put it back in. A single sip from a sandstone spring can change everything. For a nomadic tribe crossing the Negev Desert, the discovery of a clear, cool stream emerging from a rocky outcrop was not just luck, it was a mystery. The water in the surrounding wadis was often muddy and bitter, yet here it was, clean and sweet, seemingly purified by the stone itself. This observation sparked a revolution in water management, leading to one of the most elegant filtration systems ever devised. Ancient engineers realized they could replicate this natural process. They began constructing channels and basins lined with precisely cut sandstone blocks. When murky runoff or river water was channeled through these constructions, something remarkable happened. The water would seep slowly through the porous rock, leaving behind silt, debris, and even some harmful contaminants, emerging on the other side remarkably clear. The secret lies in the stone itself. Sandstone is like a hard sponge, a composite of sand grains cemented together by minerals like silica or calcium carbonate. This creates a labyrinth of microscopic pathways. As one geologist notes, these tiny pores are small enough to trap particulate matter, but large enough to allow water molecules to pass through freely. It is a perfect natural sieve. The process of building these channels was a masterclass in applied geology. Engineers first had to identify the best sandstone for the job, often preferring fine-grained varieties with high quartz content for their superior and durable filtering capabilities. Quarrying these blocks required immense skill, using wooden wedges that were soaked to expand and split the rock, or painstakingly shaping it with stone and copper tools. They created uniform slabs. The design of the system was equally sophisticated. It was not a single channel but a sequenced process. Water was first directed into a wide, shallow sedimentation basin where the heaviest silt and sand would settle out naturally. From there, it entered the main filtration channel, a gently sloping conduit completely lined and paved with the sandstone blocks. The gradient was critical, calculated to be just steep enough to keep the water moving, but slow enough to give it ample time to seep into and through the porous lining. A collection channel positioned just below the main one would then gather the now filtered water. Maintenance was a constant communal effort. Over time, the surface of the sandstone would become clogged with the very impurities it filtered. Teams would periodically scrub the blocks or even temporarily reverse the water flow to flush the system clean, ensuring its long-term operation. We see a brilliant application of this in ancient Egyptian settlements along the Nile. While they had the great river, its waters were often thick with silt, especially during the annual flood. To obtain clearer drinking water, they constructed sandstone filtration tanks near their homes. Nile water would be poured into these tanks, seep through the stone walls, and collect in a central reservoir ready for use. This was low-tech, sustainable purification at its finest. It makes you wonder, in our modern world grappling with microplastics and chemical pollutants, What could we achieve by revisiting such elegant, nature-based solutions? These systems harnessed the Earth's own materials to create purity, yet other engineers faced a different problem entirely, one where the goal was not to clean the water, but to stop it from vanishing into thin air. A lone figure in the desert pours the last of their brackish water into a shallow pit dug in the sand. They stretch a clear sheet of oiled animal skin over the hole, placing a single, clean stone at the center of the sheet. By the next morning, beads of pure, drinkable water cling to the underside of the skin, dripping steadily into a waiting cup placed below the stone. This simple act of survival is a direct echo of one of the most elegant desert technologies, the solar still. Ancient engineers near the Dead Sea, surrounded by undrinkable salt water, perfected this method of using the sun's own heat to purify water. They transformed a simple physical principle into a life-saving tool. The process relies on two fundamental forces, evaporation and condensation. The sun's energy heats the contaminated water in the pit, causing it to turn into vapor and rise. This vapor, being pure water, leaves all the salts, minerals, and impurities behind in the pit. When this warm vapor hits the cooler surface of the transparent cover, it condenses back into liquid form, just like breath fogging a cold window. The angled cover then guides these purified droplets down into a collection vessel. The construction was a study in using what was available. A pit was dug, typically 3 to 4 feet wide and about 1.5 feet deep. The bottom was sometimes lined with dark slate or even a layer of salt to absorb more solar heat, accelerating the evaporation process. The cover was the most critical component. In some places, they used large, thin sheets of clear rock crystal. In others, they used tightly woven leaves coated with plant resins to create a waterproof, transparent barrier. A small weight, like a smooth stone, was always placed at the center of the cover to create a low point where the condensation would naturally gather and drip. The yield was modest but life-sustaining. On a hot, sunny day, a well-made solar still could produce several cups of pure water, enough to keep a person alive. Historical records suggest that Roman legions on long desert campaigns used variations of this technique to supplement their water supplies, allowing them to operate far from reliable sources. It forces a powerful question. In a world increasingly concerned with energy consumption and complex purification plants, what is the untapped potential of such passive, solar-powered systems for off-grid use today? This brilliant use of natural forces to separate pure water from a contaminated source represents one pole of ancient engineering. The other pole involved moving that purified water across vast distances without a single pump, using only the unyielding pull of gravity through channels carved from the living rock. High in the Andes, a modern hiker stumbles upon a line of carved stone, a narrow channel that seems to flow down the mountainside with no beginning and no end. It is not a natural fissure. Its edges are too straight, its path too deliberate. This is the ghost of an Incan waterway, a gravity-fed conduit that once turned a mountain fortress into a living city. These channels were the lifelines of an empire built on vertical terrain, a masterful application of a simple, unbreakable law. Water always finds its lowest point. The true genius of these engineers was not in moving water, but in guiding it, persuading it to travel exactly where they needed it to go, for miles without a single pump or moving part. The design began with the most critical calculation, the gradient, too steep, and the water would rush through with destructive force, eroding the channel walls and arriving as a useless, muddy torrent. Too shallow, and the flow would stagnate, allowing silt to build up and algae to grow. Incan surveyors, using simple water levels made of hollowed wood and observation posts, mapped routes with a slope of just a few degrees, a gentle but constant decline that maintained a steady, manageable flow all the way to its destination. The construction was a testament to working with the mountain itself. Engineers selected durable igneous rocks like andesite, which could withstand centuries of freezing and thawing without cracking. They shaped these stones into precise U-shaped channels, a form that maximized the volume of water carried while minimizing friction along the walls. The joints between stones were fitted so tightly that, in many sections, you cannot slip a blade of grass between them. This precision was not just for show. It was a critical defense against leakage, ensuring that every precious drop reached its target. Modern civil engineers who study these systems express a deep admiration for their hydraulic efficiency. One noted that the consistent cross-section and smooth interior surface created a laminar flow, where water moves in parallel layers with minimal turbulence. This is the most energy-efficient way for a fluid to travel, reducing friction loss and preserving the water's kinetic energy over long distances. But the water was not sent on its journey unprepared. At strategic intervals, the Incans integrated small, carved basins that acted as settling tanks. As the fast-moving water entered these wider chambers, its speed would suddenly drop. Heavier particles of sand and sediment, suspended in the flow, would sink to the bottom. The cleaner water would then spill over a weir at the far end of the tank, continuing its journey while leaving the debris behind. This simple innovation protected the entire downstream network from clogging and erosion. Maintenance of this hidden infrastructure was a continuous, communal duty. Specific families or village groups were assigned sections of the conduit to inspect and clean. They would use specialized tools to scrape away any mineral deposits or biological growth, ensuring the channel remained smooth and efficient. The management of water rights was equally sophisticated. Water was allocated based on a complex schedule, often regulated by ceramic or stone markers that indicated how long a farmer could divert flow to their terraces. This system of shared responsibility and clear rules prevented conflicts and guaranteed that the entire community benefited. The pinnacle of this achievement is the network at Machu Picchu. A single spring on the steep mountainside above the city was captured and channeled through a stone conduit that snaked over a mile, descending nearly 250 feet to the urban center. The channel fed a series of 16 ceremonial fountains, each one a public display of the empire's mastery over water, before distributing it to residential areas and agricultural terraces. The entire city, perched in the clouds, was quenched by gravity alone. It is a humbling reminder of how a profound understanding of natural forces can create enduring solutions. This elegant reliance on gravity to move water across landscapes represents one of humanity's oldest and most reliable technologies. Yet, it makes you wonder if they could command the flow of rivers down a mountain. What other elemental forces could they have harnessed? The answer lies not in the flow of water, but in the very air we breathe, in methods that pull drinkable water directly from an empty sky. The desert rock sweats in the moonlight. As the air cools, a silent miracle unfolds across its dark surface, beads of dew forming like perspiration on stone skin. This was not magic, but another form of passive harvesting mastered by forgotten engineers, a way to pull drinking water from nothing but the cool night air. Ancient Bedouin tribes traversing the Sinai Peninsula perfected this art. They would assemble piles of porous, dark-colored rocks like basalt in natural depressions, creating dew-catching landscapes where none existed naturally. These seemingly random cairns were, in fact, meticulously designed water factories. Climatologists studying these sites explain the delicate balance required. For dew to form, the rock surface must cool past a critical threshold known as the dew point, the temperature where the air can no longer hold its invisible moisture and releases it as liquid. Dark, dense rocks like basalt are perfect for this. They possess high thermal mass, meaning they absorb tremendous heat during the day. Then, under the clear desert sky at night, they radiate that heat back into space with startling speed, their surface temperature plummeting. When the rock cools below the surrounding air's dew point, the water vapor in the air condenses directly onto the cold stone. The design of these rock piles was a science in itself. The stones were not just heaped randomly, they were often aligned to maximize their surface area to the night sky, the primary source of the cooling. The piles were strategically placed in shallow depressions that naturally collected cooler, heavier air, and sometimes they were even combined with specific, hardy vegetation. The plants would release minute amounts of water vapor through their leaves through a process called transpiration, slightly raising the local humidity right around the rocks and thereby increasing the potential dew yield. We see evidence of this clever system being used by pre-Islamic tribes on the Arabian Peninsula. In regions where even the deepest wells could run dry, these dew collection rocks provided a reliable, if modest, source of water for their most precious resource, their camels. A single site could gather enough moisture overnight to sustain a small herd, a testament to the profound understanding these cultures had of their environment. It makes you wonder, in our age of energy-intensive air conditioning and complex irrigation, could we integrate such simple, elegant principles into our own buildings? What if our cities, like these ancient rocks, were designed to sweat, to harvest their own water from the atmosphere passively? This vision of turning entire structures into water collectors points toward an even grander scale of hidden engineering, one that moved from catching dew to building colossal, unseen dams deep beneath the earth. A village in northern Kenya had given up hope. Their wells were dust and the riverbeds were bone dry. Then an elder remembered a story, a legend of an old wall hidden beneath the sand. They dug, and after days of labor, their shovels struck not rock but damp earth. Within hours, a trickle of water began to seep into the hole. They had not discovered a new source. They had awakened a sleeping giant, an ancient subsurface dam that had been silently holding its treasure for generations. This is the power of building barriers not across rivers, but inside the very earth itself. Subsurface dams are perhaps the most invisible form of water architecture. Instead of creating a visible lake that loses vast quantities to the desert sun, these structures work like a plug inserted into the underground layers of rock and sediment. Engineers in ancient Yemen and across the Horn of Africa would identify a natural underground valley, a place where water would naturally flow and collect after rare rains. They would then dig a deep trench, cutting straight down until they hit the impermeable bedrock below. This trench was then filled with a carefully engineered mixture of stone and dense clay, creating a permanent, waterproof wall that blocked the subterranean flow. The result was a hidden reservoir, a vast bubble of fresh water stored safely in the porous earth above the dam, completely shielded from evaporation. A modern water conservationist working in the Sahel region explains the profound advantage. In arid zones, a surface dam might lose half of its stored water each year simply to the heat of the sun. A subsurface dam, buried and protected, loses almost nothing. It is the difference between leaving a cup of water in the open air and sealing it inside a cool, dark cellar. The construction was a monumental feat of communal labor. It began with a meticulous geological survey, reading the landscape for clues like the tilt of rock layers or the type of vegetation that signaled a shallow water table. Once the perfect site was chosen, the real work started. Using only hand tools, crews would excavate a trench that could be hundreds of feet long and plunge dozens of feet downward. The choice of materials was critical for the dam's longevity. In areas rich with laterite, a clay-like iron-rich stone, they used it extensively. When wet, laterite is pliable and can be packed into a nearly seamless barrier. Once it dries in the sun, it hardens into a substance as durable as concrete. In granite regions, they used precisely shaped stone blocks, chiseled to fit together so tightly that they needed only a thin clay mortar to become watertight. The entire process was monitored through simple observation wells dug upstream of the dam. By lowering a marked rope, villagers could measure the rising water level, watching their invisible reservoir fill with each distant rain. A stunning example of this technology's endurance is the spate irrigation network in Eritrea. Here, a series of subsurface dams, some believed to be over 1,000 years old, captured seasonal floodwaters from mountain valleys. This trapped water would then slowly percolate through the soil, creating a sustained moisture reserve that allowed communities to grow sorghum and other crops long after the surface had dried out. It was agriculture fueled by a secret sea. This challenges us to think differently about infrastructure. What if our most vital water systems were not meant to be seen? What if resilience lies not in grand concrete monuments, but in hidden, silent walls that work with the geology of the land? This philosophy of hidden water reaches its most intimate form in the simple, life-giving rock-hewn spring. A cool breath of air whispers from a crack in a sun-baked cliff, the first sign of a miracle hidden in plain sight. This is not a random fissure, it is a rock-hewn spring, a masterpiece of engineering where the boundary between a natural water source and human creation completely blurs. The Nabateans of Petra and Roman engineers across their empire were the undisputed masters of this art. They did not merely find water seeping from the rock, they invited it out, carving and sculpting the stone itself to become a willing partner in delivering life to their communities. Their work began with a deep geological intuition. They understood that springs often emerged along fault lines, where shifts in the earth had fractured impermeable rock layers, allowing trapped water from deep aquifers to find a path to the surface. A geologist studying these sites would point out the critical role of rock type. Soft, porous sandstone was relatively easy to carve with iron chisels and stone hammers, but it could crumble and required constant maintenance. Hard, crystalline granite was a brutal challenge to shape, but once carved, its channels and spouts would endure for millennia. The choice of tool and technique was a direct response to the stone's character. The process was methodical and profound. Engineers first spent weeks or even months observing a cliff face, watching for persistent dampness or specific mosses and ferns that betrayed a consistent seepage point deep within. Once they pinpointed the source, the delicate work of enlargement began, using water to lubricate their drill points and fire to heat and fracture stubborn sections. They would carefully widen the natural fissure, not as a chaotic excavation, but as a form of architectural sculpture. They carved access tunnels just wide enough for a single person to enter for maintenance, leading to a small, vaulted chamber at the heart of the spring. Here they performed their most clever act of persuasion. They would install a carved stone spout or a bronze pipe directly into the most productive seep. This simple fixture transformed a diffuse trickle down a rock wall into a focused, controllable flow. The water was now tamed, directed into a beautifully carved basin or a waiting channel that would carry it away. But these springs were far more than just plumbing. They held immense ritual significance. In the Nabatean worldview, a spring was a sacred gift from the gods, a direct connection to the divine. The act of carving and embellishing the spring was an act of reverence. The Sick Canyon, the magnificent entrance to Petra, is a perfect example. As you walk through the towering, narrow gorge, you pass by niches and altars carved directly into the rock next to small, spring-fed basins. The water itself was part of the spiritual journey, a purification before entering the city. This sacred role was matched by a brutally practical one. These engineered springs became the beating heart of trade routes. A reliable water source in the desert was not just a convenience, it was a commodity that could support an entire economy. The city of Petra itself owed its wealth and power to its command over water. A complex network of rock-cut channels and pipelines ran along the cliffs of the Sick, collecting water from multiple springs and directing it into the city center. This system supplied public fountains, private homes, and vast underground cisterns, supporting a population of tens of thousands in the heart of the desert. It was a perfect blend of art and engineering, where the functional act of water collection was elevated into a cultural and economic triumph. The very stone of the canyon was transformed into a life-giving artery. This intimate control over a single water source represents one end of the spectrum. But what happens when the goal is not to channel a concentrated flow, but to spread water wide, to give a single drop the greatest possible reach across a thirsty land? A wall of muddy water thunders down a dry desert canyon, a destructive force that can strip the land bare in minutes. But ancient engineers saw this not as a threat, but as a resource in motion. Their solution was the water-spreading gallery, a network of broad, shallow channels carved directly into the rock to slow the flood's rage and coax its moisture deep into the earth. In the lands of ancient Mesopotamia, where flash floods from the Taurus Mountains could wipe out seasons of work, these galleries transformed catastrophe into cultivation. Engineers used locally abundant basalt and limestone, materials that could withstand the torrent's initial impact, to carve wide, gently sloped channels that fanned out across the plains. Instead of allowing water to concentrate into a single, erosive stream, the galleries deliberately spread it thin, like opening a clenched fist to reveal an open palm. One agricultural historian notes that this single innovation turned marginal lands into breadbaskets, stating that the ability to capture and infiltrate a single flash flood could mean the difference between famine and food security for an entire community. The design was a masterpiece of patient observation. It began with the construction of small check dams made from stacked rocks, placed strategically across natural drainage lines. These temporary barriers did not aim to stop the water completely, but to slow it, creating shallow pools that would then overflow into the main distribution channels. The grading of these channels was the true heart of the system. Using simple sighting tools and water levels, engineers ensured the channels had just enough slope to keep the water moving, but were shallow and wide enough to let it spill over their edges, sheeting across vast areas of prepared soil. This was not irrigation in the traditional sense. It was a method of forcing the desert to drink. The goal was not to water plants directly from a channel, but to recharge the soil moisture reservoir deep underground, creating a sustained water bank for crops to tap into with their roots. The choice of crops was integral to the system's success. Farmers planted drought-resistant varieties of barley, millet, and certain legumes, whose deep root systems could chase the moisture stored deep within the soil profile. These plants were adapted to survive on the deep watering provided by the galleries, rather than the frequent, shallow watering of conventional irrigation. Maintaining this landscape-scale system required a highly organized community effort. After each rainy season, teams would clear the channels of silt and debris carried by the floods, repairing any damage to the check dams. This was not optional work. It was a collective responsibility governed by strict rules and schedules, ensuring the system would be ready for the next unpredictable downpour. The entire community's survival depended on this shared labor. Perhaps the most striking example of this technology's power is found in the Negev Desert. Here, in what appears to be a completely barren landscape, the remains of ancient water-spreading galleries are still visible from the air. These systems captured the scant, violent rainfall, spreading it across carefully contoured fields that supported thriving agricultural settlements for centuries. They turned barren soil into productive fields not by fighting the desert's nature, but by working with its rhythm of deluge and drought. This makes you wonder, in our modern world of concrete channels and rapid stormwater discharge, what wisdom have we lost? Could reintroducing these ancient principles of slowing and spreading water help us manage urban flooding and replenish our own depleted aquifers? This idea of controlling water not by containing it, but by guiding its gentle dispersal, represents a profound shift in thinking. It sets the stage for an even more subtle art, one that captures water not from floods, but from the emptiness of the air itself. The desert breathes in the cool of the night, and on its breath water forms. This paradox, pulling liquid from arid air, was harnessed by engineers who built condensation traps, subterranean chambers that turned humidity into a harvest. In the coastal deserts of ancient Persia and Egypt, where daytime heat gives way to thick, moisture-laden night air, these structures were masterpieces of passive thermodynamics. An environmental scientist studying them explains the core principle that when warm, humid air enters a space cooled by the massive thermal mass of the Earth, it is forced to drop its moisture, just like a cold glass sweats on a summer day. The construction was a deliberate process. First, a large pit was dug, often reaching depths of 15 or 20 feet to access the consistently cool temperatures of the subsoil. The walls were then lined with dark, heat-absorbing rocks like basalt. These rocks would soak up the sun's energy all day, but the key was their placement underground, where the surrounding earth would slowly draw that heat away through the night, leaving the rock surfaces significantly colder than the night air. Builders would often mix organic matter, such as straw or compost, into the chamber. As this material decomposed, it released moisture, artificially raising the humidity inside the trap and increasing the potential yield. The orientation was critical. Air shafts were carefully positioned to face the prevailing nighttime winds, funneling the damp air directly into the chilled chamber. Inside, the vapor would condense on the cold rock walls, forming droplets that trickled down into carefully carved drainage channels. These channels, lined with impermeable clay, would then guide the collected water to a central underground reservoir. Some builders even scattered salt crystals on the floor, as the salt would absorb moisture from the air during the night and release it as the chamber warmed slightly, adding another layer of efficiency to the process. The most stunning examples are the yakhchuls of Iran, towering conical structures that functioned as ancient refrigerators. Beneath these iconic domes lay deep underground storage pits that utilized this exact condensation principle. Remarkably, these structures could produce not just liquid water, but actual ice during the summer months, a testament to their incredible cooling power. This makes you wonder, in an era of energy-intensive dehumidifiers and air conditioning, what if our buildings were designed to passively condense atmospheric moisture as a supplementary water source? This vision of capturing every possible drop leads to another grand strategy, one that focuses not on the air, but on giving water every opportunity to sink back into the earth through the simple, profound technology of the percolation tank. A modern water scout mapping arid regions with satellite imagery noticed a strange circular depression hidden under a thicket of thorny acacia. From the ground, it looked like nothing more than a shallow dip in the land, but when she cleared the brush, her hands found the truth. the smooth, carved rim of a massive stone basin. This was no natural formation. It was a forgotten percolation tank, a secret portal designed not to hold water, but to send it on a journey deep into the earth. Ancient engineers across India and the Middle East mastered this counterintuitive art. While others built cisterns to keep water in, they built these tanks to let it go, slowly and deliberately, fighting evaporation by hiding the water where the sun could never reach it. A hydrologist studying these systems explains the core benefit. When water percolates slowly through layers of soil and rock, it undergoes a natural purification process, filtering out impurities and becoming pristine groundwater. This slow recharge also sustains springs and wells for months after the rain has gone, providing a stable, reliable supply instead of a fleeting surface pool. The engineering began with a critical choice of location. Scouts would identify natural catchment areas, places where rainwater already gathered and flowed. But the key was the geology beneath. They needed a basin carved into an impermeable layer of rock, like shale or dense clay, to prevent the water from simply draining straight down and being lost. Instead, the tank acted as a temporary holding cell, its floor and walls sealed by the natural stone, forcing the water to exit only through a carefully prepared infiltration gallery at its base. The construction was a meticulous, multi-stage process. First, workers would excavate the large, saucer-shaped basin directly into the bedrock. The floor was given a very slight, almost imperceptible slope, not to drain water away, but to guide it toward a central collection point where the main filtration system began. There, they would dig a deep pit and fill it with layers of graded materials, large stones at the bottom, then smaller gravel, then coarse sand, creating a natural sieve that cleaned the water as it began its descent. The social governance of these tanks was as sophisticated as their engineering. In many communities, the water collected was considered a shared trust. Village councils established strict rules for its use, often tied to the tank's capacity, which was calculated through generations of observation. They knew how much rainfall a single storm might bring and how many families the resulting groundwater could support. Maintenance was a communal duty, with families taking turns to clear silt and debris from the basin before each rainy season, ensuring maximum infiltration. A breathtaking example of this dual-purpose design exists in the temple tanks of Tamil Nadu. These magnificent, ornately carved stone reservoirs, known as pushkarinis, were central to Hindu temple rituals. Devotees would perform ceremonial baths in their waters, an act of spiritual purification. Yet, simultaneously, the tanks were functioning percolation engines. The water used in rituals would slowly seep through the tank's foundation, recharging the local aquifer and providing clean groundwater for the entire temple town. It was a perfect fusion of the sacred and the practical, where every drop served both the spirit and the soil. This vision of decentralized, earth-integrated storage makes you reconsider the very shape of water security. What if our solutions were not massive, centralized reservoirs, but thousands of such small, hidden recharge points scattered across the landscape? To complete this cycle of hidden water, one final innovation was needed, a way to bring that deeply stored water back to the surface without endless labor, using a force as timeless as the desert wind itself. A timeless rhythm echoes across the desert, the slow, groaning turn of a wind-driven pump heaving water from the depths. In ancient Persia, engineers achieved a marvel of sustainable energy, crafting pumps from stone and wood that ran for centuries on the desert's breath. They began with a simple predecessor, the shaduf, a long pole with a rock counterweight that allowed a single person to lift water from a shallow well. But their ambition grew with the wind. They envisioned a system that could work endlessly without human fatigue, tapping into the relentless desert winds. Mechanical historians trace the evolution to the Sakya, a beast of burden that was then liberated from the ox. The innovation was a vertical wind wheel, its sails made of woven reed or wood, catching the wind to turn a central axle. This axle was connected to a massive, horizontally mounted gear, painstakingly carved from a single piece of local granite or sandstone. The teeth of this stone gear meshed with the pins of a vertical wheel, converting the horizontal rotation into a powerful vertical one. From this vertical wheel, a loop of rope or a chain of pots was suspended, dipping down into the well and rising again, each pot spilling its contents into a channel at the apex of its journey. The choice of materials was a masterstroke of appropriate technology. While wooden gears required frequent replacement under the constant strain, the stone gears, though far more laborious to quarry and carve, could endure for generations. The entire system was a study in balancing forces. The weight of the descending, empty pots helped to pull the full ones upward, while the massive stone gear acted as a flywheel, smoothing out the jerky, variable power of the wind to maintain a steady, rhythmic lift. This was not a machine that fought nature, but one that danced with it. We see this beautifully illustrated in the Egyptian oases of the Western Desert. Here, networks of these wind-driven pumps lifted water from deep wells to irrigate vast groves of date palms. The water, once raised, was channeled through a network of shallow ditches that spread the life-giving resource across the sun-scorched land. The entire system created a self-sustaining agricultural ecosystem, powered by a force that cost nothing and never ran out. It makes you wonder, in our pursuit of complex, high-energy solutions, have we overlooked the elegant synergy of using one natural force to manage another? This graceful lifting of water represents one of the final steps in the ancient cycle, bringing the hidden reserves back to the surface. But once the water was drawn, another challenge remained, one of clarity and purity, handled with equal ingenuity in the quiet, patient space of the sedimentation basin. After a desert sandstorm, the world is left choked with dust, and the few remaining water sources turn to thick, undrinkable mud. For a nomadic tribe, survival in the hours that follow hinges on finding a place where that water can become clear again. Their salvation often lay in a simple, profound technology carved directly into the landscape, the rock sedimentation basin. These were not mere puddles. Ancient engineers across the Sahara and Gobi deserts designed them as multi-stage purification factories, where water was persuaded to clean itself through the patient force of gravity. The principle is timeless. When fast-moving, silt-laden water enters a wide, calm basin, its speed drops instantly. Heavier particles of sand, clay, and organic matter, no longer suspended by the water's energy, simply sink to the bottom. What remains is visibly clearer, healthier water, ready for drinking or irrigation. A water quality expert working with arid communities today notes the direct impact, stating that reducing turbidity through simple sedimentation is the first and most critical step in preventing waterborne diseases, dramatically improving community health where modern filtration is not an option. The construction of these basins was a masterclass in hydrology. Engineers began by selecting a site with a natural slight incline. They would then excavate not one, but a series of interconnected chambers directly into the bedrock. The first and largest chamber was the primary settling tank. Here, the coarsest sediment would drop out within the first few hours. The water would then spill over a low weir, a carefully leveled stone wall, into a second, smaller chamber. This secondary basin allowed finer silt to settle over a longer period. The final stage often involved a filter bed. the floor of the last chamber was paved with layers of graded materials, large, fist-sized rocks at the bottom, then smaller pebbles, and finally a layer of coarse sand. As the water percolated up through this natural sieve, even more fine particles were removed. The entire system was designed with maintenance in mind. The basins were periodically taken offline and manually cleaned. Communities would work together to scoop out the accumulated silt, which was not waste, but nutrient-rich soil often used to fertilize nearby gardens. In some advanced designs, engineers introduced specific aquatic plants into the final chambers. Their roots created a dense mat that trapped microscopic particles and absorbed excess nutrients, providing a final, living polish to the water. We see a brilliant application of this in ancient Carthaginian settlements. Located in North Africa, they faced constant challenges from silty runoff. Their engineers built extensive networks of rock-cut sedimentation basins on the outskirts of the city. Runoff from the hills was captured and channeled into these basins before being allowed to enter the main storage cisterns. This crucial pre-cleaning step ensured that the water supplying the famed fountains and baths of Carthage was remarkably free of the sediment that could clog their intricate plumbing and sicken the population. It makes you reflect on our own modern water systems. So many of our reservoirs today struggle with high turbidity, especially after heavy storms, requiring expensive chemical treatments and constant dredging. What if we revisited this ancient idea of letting the landscape itself do the work of primary filtration? This elegant, low-energy approach to achieving water clarity represents a fundamental piece of the puzzle. Once the water was clean, the next challenge for these master engineers was to protect it, not just from the impurities it carried, but from the relentless, thirsty sky above. The desert drinks like a giant with a hidden throat, and ancient engineers learned how to guide its sips. Across the vast emptiness of the Arabian Peninsula, they built aquifer recharge mounds, porous pyramids of stone that acted as giant funnels for the rain. These were not monuments to gods or kings, but to the unseen waters below, a deliberate effort to feed the hidden ocean beneath the sand. When a rare, violent storm swept across the land, most of the water would simply rage across the hard-packed surface and vanish. But these carefully placed rock piles changed that destiny. They broke the water's momentum, capturing the runoff and giving it a deliberate pathway straight down into the aquifer. Groundwater modelers who study these ancient systems note their profound impact on drought resilience. By artificially boosting the natural recharge rate, a community could ensure their wells and springs would continue to flow long after the last rain had evaporated, turning a seasonal gift into a year-round resource. The process began with a deep understanding of the land's hidden anatomy. Scouts would identify natural recharge zones, areas where the geology allowed surface water to percolate down to the water table more easily. These were often at the base of rocky outcrops or in the gravel-filled beds of ancient, dry rivers. Once the perfect site was chosen, construction began. The mound's core was built from the most permeable rock available, often light, vesicular volcanic scoria, which is essentially a hard, natural sponge. This core was then surrounded by an outer layer of larger, heavier stones that protected the delicate interior from erosion while still allowing water to pass through. The shape of the mound was itself a piece of hydraulic engineering. Many were built with a gentle, concave depression on their windward side, designed to catch and pool runoff. The entire structure was often elliptical, aligned to intercept the flow of water across the landscape, maximizing the amount of moisture it could capture and guide downward. To further enhance the system, engineers sometimes planted deep-rooted, drought-tolerant shrubs on and around the mounds. These plants helped to stabilize the structure with their root networks, and when they shed leaves, the organic matter improved the soil's ability to absorb and retain moisture right at the critical infiltration point. A stunning example of this integrated approach is found in the afflage systems of pre-Islamic Oman. Here, recharge mounds were strategically built in the highlands, far from the farms and cities in the valleys. Their sole purpose was to capture mountain runoff and direct it into the same underground layers that fed the distant springs. This long-distance engineering meant that a rainstorm in the hills could, weeks or months later, result in a stronger, more reliable flow in the water channels miles away, a testament to planning on a geological timescale. It makes you wonder, as many modern aquifers are being drained faster than nature can refill them, could these simple, low-cost structures offer a way to help the earth heal itself? This patient work of replenishing deep reserves was only one half of the equation, for the water that was so carefully guided underground would one day need to be brought back into the light. A village elder dips a dried gourd into a shallow well, his movements slow and practiced. He does not lift it. Instead, he leans his weight on a long pole, and a heavy stone tied to the other end rises from the ground. The water-filled gourd swings up as if by magic, light as a feather, and he pours it into a waiting irrigation channel. This is the Shadoof, a lever-powered water lifter so efficient that its basic design has remained unchanged for over 4,000 years. It transformed back-breaking labor into a simple, rhythmic motion, a testament to the power of counterweights. The core principle is pure physics, a balance of forces. A horizontal beam is mounted on a pivot like a seesaw. On one end hangs a bucket, and on the other, a dense rock counterweight, often carved from basalt or granite. The weight of the rock nearly balances the weight of the empty bucket. When the farmer pulls the bucket down to fill it, the counterweight rises. Letting go, the heavy rock falls, and the full bucket effortlessly ascends. The force required from the human operator is minimal, a gentle guiding pressure rather than a strenuous lift. An anthropologist studying ancient farming communities notes that the Shadoof was more than a tool, it was a social organizer. Its use created a predictable, sustainable rhythm for irrigation, allowing families to manage their water allotments fairly and efficiently. The entire system fostered a culture of shared maintenance and precise water distribution that was critical for survival. Building one was an exercise in applied mechanics. The pivot point, or fulcrum, had to be positioned with careful calculation. For a deeper well, the beam was made longer on the counterweight side, providing more leverage to lift the heavier, water-laden bucket from the greater depth. The beams themselves were crafted from resilient, locally sourced acacia wood or, in some cases, shaped from solid stone. The counterweights were the heart of the machine. Engineers selected the densest rocks available, sometimes shaping them into smooth, aerodynamic forms to reduce air resistance during their constant, rhythmic fall. Once lifted, the water was never wasted. It was poured into a network of meticulously graded channels that carried it to specific plots of land, ensuring every drop served a purpose. This basic design spawned regional variations across the ancient world. In Egypt, the classic Shadoof with its distinctive frame support became an iconic symbol of Nile agriculture. In parts of India, a similar device called the Picchu used a long bamboo pole and an earthen pot, operated by two people in a coordinated, dancing motion. The scale of their impact is best understood along the banks of the Nile River. Here, thousands of these devices worked in concert, creating a symphony of lifting and pouring that raised water from the river to the higher fields. This continuous, low-energy irrigation is what allowed Egyptian civilization to flourish for millennia, turning the desert fringe into one of the most productive agricultural landscapes in the ancient world. It forces a powerful question in our pursuit of higher yields and automated systems. What profound efficiencies have we forgotten? This elegant use of balance to conquer gravity finds a curious parallel in another ancient method, one that captures water not from below, but from the air itself, using enhancements to the very fog nets we explored earlier. A dense mist clings to the highland forest, and every stone glistens with a perpetual, silent rain. In these cloud forests where fog is a constant companion, ancient Andean cultures observed a subtle phenomenon and learned to amplify it. They noticed how water dripped steadily from the leaves of certain trees and the surfaces of moss-covered rocks long after the fog itself had moved on. Their innovation was deceptively simple. They began placing carefully arranged piles of porous rock and building low walls beneath the canopies of the tallest trees. These were not random constructions. They were fog drip enhancements designed to catch every possible drop that nature provided. Ecologists studying these micro-water cycles note the critical role of epiphytes, the mosses and bromeliads that coat the trees. These plants act like living sponges, absorbing moisture directly from the air. The rocks placed below serve a dual purpose. Their cold surfaces encourage additional condensation from the saturated air, and their rough, porous texture provides a massive surface area for droplets to form and merge. The technique required a deep understanding of the local environment. Engineers would first identify the most fog-prone sites, often windward slopes at a specific altitude where clouds made consistent contact with the land. There, they built extensive arrays of volcanic rock, choosing varieties like scoria for its high porosity and ability to hold moisture. The rocks were often stacked in loose, open piles rather than solid walls, allowing air to circulate through them and maximizing the condensation surface. Channels carved from wood or stone would then be positioned at the base of these rock piles, guiding the collected drip water into storage jars or small, terraced agricultural plots. The choice of rock was a science in itself. A highly porous stone filled with tiny air pockets cools down rapidly at night. When the warm, moisture-laden fog passes over it, the temperature difference forces the water vapor to condense into liquid on the cold stone surface. This process can yield a surprising amount of water over time, supplementing rainfall in a climate where liquid precipitation might be scarce. This method was often combined with the terracing seen on the mountainsides. The enhanced fog drip would provide a slow, steady supply of moisture to the upper terraces, reducing the reliance on channeled water from distant springs. A stunning example of this synergy exists in the Laura Silva forests of the Canary Islands. These ancient, mist-shrouded woodlands are a relic of a tertiary-era ecosystem. Here, pre-Hispanic inhabitants used rock enhancements to capture the constant fog drip, creating a hidden water infrastructure that supported their settlements and preserved the unique, moisture-dependent flora around them. They were not just taking from the environment, they were participating in it, building structures that mimicked and augmented the natural water cycle. This invites a profound reflection on our own approaches to resource management. What if, instead of always imposing our own designs, we first learn to read and enhance the patterns that nature has already perfected? This philosophy of working within the landscape finds its ultimate expression in a technology that does not catch water, but gently persuades it to stay through the subtle power of the seepage barrier. A flash flood does not have to be a destructive force. In the canyons of ancient Yemen, when a wall of muddy water roared down a dry wadi, it was met not with resistance but with an invitation. Low walls of stacked stone built directly across the watercourse would slow the torrent's rage, persuading it to pause and sink deep into the thirsty ground. These were rock seepage barriers, and their purpose was to turn a fleeting disaster into a lasting resource. Desertification experts today point to these structures as a primary defense against soil loss. By slowing the water, they drastically reduce its power to strip away the fertile topsoil, while simultaneously forcing moisture into the local aquifer, recharging groundwater reserves and fighting the desert's expansion. The construction was a masterclass in simplicity and stability. Engineers did not seek to create an impermeable dam. Instead, they carefully aligned a series of barriers across the natural flow path of the water. The walls were built with interlocking rocks, meticulously chosen and stacked, often without any mortar at all. This deliberate design created a structure that was strong enough to withstand the flood's initial impact, yet porous enough to allow a controlled amount of water to seep through, filtering out silt and debris as it passed. The true genius lay in the spillways. The central section of the barrier was often built slightly lower than the sides. When the water volume became too great, it would safely overflow through this designated channel, preventing the structure from being overwhelmed and washed away. This ensured the barrier would survive to capture the next flood and the next for generations. Building and maintaining this network was a profound act of community labor. Entire villages would come together to gather stones, stack the walls, and after each rainy season, perform the essential repairs. It was a shared responsibility, a collective investment in their future water security. The system's success is vividly illustrated in the Dra Valley of Morocco. Here, countless rock seepage barriers were built across the valley floor, capturing the unpredictable flows from the Atlas Mountains. This captured water would slowly percolate downward, sustaining vast groves of date palms that otherwise could never have survived in the arid landscape. It was agriculture fueled not by surface rivers, but by a hidden, recharged water table. This makes you wonder, in our modern world where we often channel stormwater away as quickly as possible, what if we instead designed our landscapes to slow it down and let it sink in? This ancient strategy of gentle persuasion stands in stark contrast to another method, one that sought purity not through seepage, but through the very substance of stone itself. The sun can cook water clean. This simple truth was harnessed by ancient nomads who turned dark, heat-absorbing stones into portable purification systems. They used slate or black basalt, rocks that act like solar sponges, soaking up intense thermal energy throughout the day. The process is a form of solar distillation, a method that separates pure water from salts, minerals, and even some biological contaminants. A chemist would explain that when impure water is heated, it turns to vapor, leaving all its impurities behind. When that vapor then contacts a cooler surface, it condenses back into liquid, now in its purest form. The ancient setup was elegantly simple. A sealed pit was dug and lined with these dark, sun-heated rocks. Brackish or contaminated water was then poured over them. The scorching stones would instantly cause the water to flash into steam. Above this, a cover was placed, sometimes a large, cool rock slab, sometimes a dome of woven plant leaves. As the steam rose, it would condense on this cooler surface, and the resulting pure droplets would be channeled into a collection vessel. The color of the rock was critical. Dark, dense stones reached much higher temperatures than lighter-colored ones, dramatically increasing the efficiency of the vaporization process. Builders also had to consider safety, ensuring the pit was deep enough and the rocks stable to prevent dangerous collapses from the rapid thermal expansion. We see echoes of this technology in the practices of some Australian Aboriginal groups. Historical accounts describe the use of heated stones placed directly into natural water holes. The stones would heat the surrounding water, encouraging evaporation, while cooler leaves or bark placed overhead would capture the condensation, providing an emergency source of cleaner water in a harsh landscape. This makes you reflect in a survival situation or in regions with contaminated water sources. How many lives could be saved by revisiting such an elegantly simple, energy-free purification method? This brilliant act of pulling purity from poison using only stone and sunlight represents a profound mastery of elemental forces. It sets the stage for a final, grand strategy, one that moves beyond cleaning water to fundamentally reshaping the underground world itself through the silent work of infiltration shafts. A lost traveler stumbling through the heat haze might find their salvation in a simple hole in the ground. They would lower a rope and descend into a cool, damp darkness, not knowing they were entering the mouth of an infiltration shaft, a direct line to the desert's hidden heart. These vertical tunnels, carved through solid rock by engineers in ancient Persia and North Africa, were masterpieces of hydrological speed. Their purpose was singular: to bypass the thirsty sun entirely by channeling precious surface water from flash floods straight down into the deep aquifers below. This was not storage, it was immediate, high-speed banking, a desperate race against evaporation. One hydrogeologist studying these systems notes the profound trade-off, stating that while direct recharge is incredibly efficient, it carries the risk of introducing surface contaminants into the pristine groundwater if not managed with extreme care. The ancient builders understood this balance instinctively. The engineering began with a precise geological survey. Teams had to locate a spot where a deep, water-bearing aquifer lay beneath a sealing layer of impermeable rock, like shale or dense clay. Their goal was to punch a hole straight through that seal, using hand augers and fire-setting techniques to fracture the stubborn stone. They would drill a shaft sometimes over 100 feet deep. The real danger was collapse. As they dug through unstable sand and gravel layers above the bedrock, they lined the shaft's walls with interlocking rings of stone or baked clay, creating a permanent, rigid sleeve that held back the crumbling earth. At the surface, the system was equally clever. The inlet to the shaft was not just an open hole. It was often a broad, shallow basin carved into the rock, designed to slow the violent rush of a flood. This basin acted as a preliminary settling tank, allowing the heaviest silt and debris to drop out before the clearer water was allowed to enter the shaft. The grading of the inlet channel was critical, calculated to control the flow rate and prevent the shaft itself from being scoured and eroded by the torrent. Monitoring water quality was a constant, vigilant practice. Upstream of the main infiltration shafts, communities often maintained smaller, secondary shafts used solely as observation wells. By lowering a marked rope, they could check the clarity and depth of the water percolating downward, ensuring the aquifer was being fed with relatively clean water. This shared resource required clear rules to prevent conflict. Access to the shafts, especially after a rare rain, was governed by strict schedules. Stone markers placed near the inlets would indicate which family or village had the right to divert floodwaters into the shaft at a given time, a system that prevented hoarding and guaranteed equitable replenishment for all. The Fagara systems of the Algerian Sahara provide a stunning example of this integrated genius. Here, infiltration shafts were dug in the highlands to capture sporadic rainfall. This recharged aquifer would then feed the very same water table that supplied the long, gravity-fed Qanat tunnels miles away in the valleys. It was a complete, self-reinforcing cycle, where one technology fed the other, sustaining oasis cities in the world's most unforgiving terrain. It compels a modern question, as many of our own aquifers are pumped to dangerously low levels. What if we dedicated ourselves to such rapid, targeted replenishment? How quickly could we reverse the decline of our most vital hidden reserves? This act of sending water on a one-way trip deep into the earth represents a profound faith in the future. But once that water was safely stored below, another challenge emerged, one of elegant extraction, solved by the graceful, arching form of the counter-weighted lift. A camel walks a slow, patient circle around a stone arch rising from the desert floor. With each of its steps, a heavy rope tightens over a smooth groove in the arch, hauling a full bucket of water from the well's cool darkness below. This was the rhythm of the water-lifting arch, a fusion of animal strength and elegant engineering that turned a well into a continuous fountain. Roman and Byzantine engineers, masters of arid settlement, perfected this design. They used the most abundant material available, local limestone and sandstone, to construct these enduring monuments to function. An architectural historian would note the profound advantage of stone over wood in such a dry climate. While wooden supports would warp and splinter under the relentless sun, a well-built stone arch could stand for 1,000 years, its strength only growing as the mortar cured and the stones settled into a single, unified structure. The mechanism was a masterpiece of coordinated effort. First, the arch itself was built directly over the mouth of the well, its foundations dug deep into the stable earth to bear the immense shifting loads. A massive, precisely carved stone pulley was then set into the apex of the arch. Through this pulley ran a rope or a leather strap with a bucket tied to one end and a carefully calibrated rock counterweight attached to the other. The counterweight was the secret to its efficiency. Its mass was calculated to nearly balance the weight of the empty bucket, meaning the camel or ox walking downhill only had to overcome the difference to lift the full, heavy container. This was not a series of hard lifts, but a smooth, cyclical flow. As the animal walked its endless path, one bucket would rise while another descended, creating a near-constant stream of water being poured into a waiting channel. The designs were adapted to the need. For a shallow well, a single, smaller arch sufficed. For deeper wells requiring greater lift, engineers built taller, more robust arches with heavier counterweights and longer ropes, a testament to their understanding of leverage and force. These structures were more than just machines. They were cultural landmarks. The stones of the arch were often carved with symbols of protection and fertility, a blessing for the life-giving water they helped provide. We see this beautifully illustrated in the Syrian desert castles, remote military outposts that had to be self-sufficient. Here, water-lifting arches were not a convenience, they were a strategic necessity. Their reliable operation supplied entire garrisons, allowing Roman legions to hold the frontier in landscapes that offered no other concessions. This seamless interface between human need, animal power, and stone mechanics represents a harmony often lost in our automated world. It makes you reflect on the quiet collaboration required for survival, a partnership that extended even to capturing water from the most intangible of sources, the very humidity in the air. A desert gardener notices a single, stubborn melon vine thriving where all others have withered. Curious, she digs down and her fingers find not just dry soil, but a buried cache of porous, moisture-beaded stones. She has unknowingly revived an ancient subsurface moisture trap, a hidden sponge that pulls water from the very air to feed plant roots. This forgotten technique transformed patches of barren ground into micro-oases, a quiet revolution in arid farming. Across ancient Mesoamerica and the expansive Sahara, cultures mastered this art of planting in what amounted to an underground dew-catcher. They utilized rocks like volcanic pumice or tuff, stones so full of air pockets they act like mineral sponges, capable of absorbing and holding surprising amounts of atmospheric moisture. An agronomist studying the method explains the physics at play, noting that these porous rocks are hygroscopic, meaning they naturally attract and bind water molecules from the surrounding soil air. When the soil dries out during the day, the rocks slowly release their stored moisture, creating a sustained, damp environment right at the root zone. The construction was a deliberate, layered process. First, workers would dig a pit, typically 2 to 3 feet deep and equally wide, directly where a tree or crop was to be planted. This pit was then filled with a mixture of crushed, porous rock and the original soil. The crushed rock provided the vast surface area for condensation, while the soil helped to integrate the system with the surrounding earth and support root growth. The depth of the trap was calibrated to the local climate. In extremely arid regions, pits were dug deeper to access cooler, more stable subsoil temperatures where condensation occurs more readily. In areas with slightly more humidity, shallower pits sufficed, capturing moisture from the daily temperature swings nearer the surface. To boost the system's efficiency, engineers often combine the rock layer with a thick blanket of organic mulch on top. This mulch, made from straw, dried leaves, or even animal manure, served a dual purpose. It shaded the soil, reducing surface evaporation, and as it decomposed, it released its own moisture and nutrients, further enriching the hidden reservoir below. A stunning adaptation of this principle is seen in the chinampas of Mexico. While famously known as floating gardens in lake-rich areas, the same hydrological intelligence was applied in drier regions. There, farmers would create raised planting beds underlain by deep trenches filled with porous rock. These subterranean chambers would harvest nighttime humidity, providing a consistent water source that allowed crops to flourish despite scant rainfall. It makes you wonder, could our own urban gardens and city parks be redesigned with such simple, self-watering cores beneath the surface, reducing the need for constant irrigation? This subtle art of creating hidden moisture banks represents a deep collaboration with the atmosphere itself, a prelude to the grander scale of water guidance found in rock-hewn canals. A stone river flows through the desert, its current silent and eternal. These are not waterways of earth and clay, but rock-hewn canals, channels carved with immense patience directly into the living bedrock of the land. To walk alongside them is to witness the ultimate expression of human determination, a permanent solution to the problem of moving water across vast, sun-scorched distances. The Hohokam people of ancient Arizona were masters of this art. In a landscape defined by scarcity, they sculpted hundreds of miles of these canals from the local sandstone, creating an agricultural network so vast it supported one of the largest populations in North America for over 1,000 years. Their work began with an almost supernatural precision. Lacking modern tools, they aligned these massive engineering projects using celestial navigation, sighting routes by the fixed positions of stars to ensure a gradient so consistent that water would flow for miles without a single pump. An irrigation engineer studying these systems today might point out a fundamental advantage. An earthen canal is constantly losing water to seepage and requires endless maintenance to clear vegetation and repair eroded banks. A canal carved from bedrock, however, is nearly permanent. Its smooth, solid walls present minimal friction and almost zero leakage, delivering a far greater percentage of the water to its intended destination. The construction was a multi-generational endeavor. Surveyors first mapped the route, using water-filled trenches as simple levels to confirm the gentle, unbroken decline. Then the quarrying began, using tools of hardened stone and fire to fracture the rock. Crews would painstakingly peck and grind the channel into existence, inch by grueling inch. The gradient was everything, a calculation of breathtaking accuracy. Too steep, and the water would gain destructive speed, eroding the channel floor. Too shallow and silt would settle, clogging the artery. They achieved a slope of often less than 1%, a drop of just a few feet per mile, a testament to their profound understanding of hydraulics. But a canal is more than a ditch, it is a managed system. At critical junctions, they integrated carved stone gates. These sliding slabs of rock could be raised or lowered to control the flow, diverting water into secondary channels to feed different fields or communities according to a strict schedule. This control was vital, as water shares were a constant source of potential conflict. The distribution was governed by intricate social codes and overseen by water masters, individuals entrusted with the power to open and close these stone gates to ensure a fair allotment for all. This intricate relationship between water and society finds a stunning, mysterious expression in the Nazca lines of Peru. The famous geoglyphs, those vast figures etched into the desert pavement, were not created in isolation. They were part of a larger hydrological landscape. Recent archaeological surveys have revealed that the Nazca built extensive networks of rock-cut canals and spiral-shaped aqueducts known as puquios to tap into underground aquifers. This water system sustained the population that created the giant drawings, suggesting the lines themselves may have been a form of ritual mapping, a spiritual reflection of the life-giving water channels that snaked beneath the sacred plain. To see these canals today, their stone channels still holding their perfect line after centuries of abandonment, is to understand a different kind of time. It speaks to a philosophy of building for the ages, of investing labor in an infrastructure meant to outlast its creators. This permanence carved in stone makes our modern systems of pipes and concrete seem fleeting by comparison. It forces a question: if they could command the flow of water with such lasting authority, what other elemental forces could they manipulate with similar subtlety? The answer may lie not in the stone itself, but in the air above it, in a technology that used temperature itself to move water without a single moving part. A cool breath seems to whisper from the stone itself, a gentle exhalation in a forgotten cave where the dark walls glisten with perpetual dew. This natural phenomenon, where cool rock sweats pure water from seemingly nothing, is the heart of a forgotten art. Ancient engineers observed this carefully and realized the air itself could be a conveyor, carrying moisture from one place to another if only they could persuade it to move. They discovered they could build a breath into the landscape, a thermal siphon that used the sun's heat as its only engine. Scholars in ancient Greece and the Middle East documented these principles, designing structures that functioned like a set of stone lungs. They understood that heating air causes it to expand and rise, while cooling it makes it contract and sink, creating a constant, silent circulation. This convection current, once established, becomes a self-perpetuating pump with no moving parts. A physicist studying these systems would note their elegant efficiency in stable, arid climates, where the temperature difference between day and night is stark and reliable. The sun provides all the power needed to keep the cycle turning. The construction was a masterclass in applied thermodynamics. Engineers would build a dual-chambered structure, often partially buried. One chamber was designed as a heat absorber. Its walls were built from dark, dense rocks like basalt, painted black or covered in soot, and oriented to face the full force of the sun. The other chamber served as a heat rejector. It was built from light-colored, reflective stones like limestone or even polished marble, and was carefully shaded or buried deep in the earth to remain as cool as possible. These two chambers were then connected at both the top and the bottom with carefully carved stone tunnels. Here is where the magic happened. The sun would bake the dark rocks in the hot chamber, superheating the air inside. This hot air would then expand and rise, rushing out through the upper tunnel. Its departure created a slight vacuum, pulling cool, dense air from the cold chamber in through the lower tunnel to replace it. This cool air, in turn, would be warmed by the dark stones, beginning the cycle anew. But the true purpose was hidden in the air itself. The cool air pulled into the hot chamber was often laden with invisible water vapor from the surrounding environment. As this damp air was heated and cycled through the system, it would eventually be drawn into the cold chamber. There, the sudden chill would force the vapor to condense on the cold stone walls, just like breath on a winter window. Channels carved into the floor of this cold chamber would then collect the beads of newly formed water, guiding it into a waiting reservoir. A stunning historical application of this principle is found in the tombs of some Egyptian pharaohs. Deep within these structures, architects used variations of thermal siphoning not to collect water, but to control the destructive humidity that could damage wall paintings and artifacts. By creating passive airflows, they kept the interior atmosphere stable and dry, preserving their treasures for millennia. This makes you wonder, in our modern world of energy-hungry dehumidifiers and air conditioning, what could we learn from this passive, silent climate control? How might we design our buildings to breathe in a way that manages moisture and even harvests it from the air? This profound understanding of how to move air and moisture with nothing but temperature differences represents a pinnacle of low-tech brilliance. It set the stage for another innovation, one that worked not in hidden chambers, but in the open air, using cleverly placed stone barriers to spread water wide across a thirsty land. A sudden desert rain does not have to be a lost cause. When a rare storm breaks over the arid landscape, water-spreading weirs transform its destructive rush into a gentle, life-giving soak. These low dams of stacked stone built across seasonal streams are masters of persuasion, not force. They do not block the water, they invite it to slow down, to spread wide, and to sink deep into the parched earth. The immediate effect is a visible resurrection. Within days of a captured flow, a strip of land downstream erupts in a carpet of green as dormant seeds awaken to the sustained moisture. This is not magic, it is hydrology in action. Ancient engineers across the Sahel and the American Southwest perfected this art, building these structures in elegant series. Each weir in the sequence takes a little more speed from the torrent, spreading the water a little further, until the flood's energy is spent not on erosion but on infiltration. A restoration ecologist working in these regions notes the cascading benefits, explaining that by slowing the water, weirs dramatically increase the time it has to percolate into the soil profile. This recharges groundwater, supports deeper-rooted native plants, and creates pockets of habitat that boost local biodiversity, turning a barren wash into a linear oasis. The design begins with a strategic eye. Builders selected locations at stream confluences or where the natural channel widened, places where the water's force was already beginning to dissipate. Using stones gathered from the surrounding area, they stacked them into low, curved walls, often without any mortar. The stability came from the careful interlocking of the rocks, each one chosen for its shape and weight. A critical feature was the spillway. The central portion of the weir was intentionally built a few inches lower than the sides. This ensured that during an exceptionally large flood, water would safely overflow through this designated channel, preventing the structure from being blown out by the pressure. The weir's height was a direct response to local conditions. In areas with frequent, small rains, lower weirs sufficed to capture the modest flows. In canyons prone to violent flash floods, builders constructed taller, more robust weirs capable of withstanding the initial shock. But the stone alone was not enough. To lock the weir in place and prevent the water from scouring around its ends, engineers planted deep-rooted native grasses and shrubs along its wings. These plants stabilized the soil and created a living barrier that further slowed and filtered the flow. The maintenance of these systems was a community ritual. After each rain, people would walk the channels, checking for damage, clearing debris from the spillways, and reinforcing any loose stones. This shared vigilance guaranteed the weirs would be ready for the next unpredictable downpour. The Zuni people of New Mexico offer a stunning example of this technology's endurance. For centuries, they built extensive networks of water spreading weirs across their high desert landscape. These structures captured the runoff from summer monsoons, spreading it across carefully prepared agricultural fields. This patient management of scarce water allowed them to grow corn, beans, and squash in a land that received less than 12 inches of rain a year, sustaining their culture through cycles of drought. It makes you reconsider the very shape of water security. Instead of channeling it away, what if our goal was to slow it down, to let every drop meet the soil? This philosophy of gentle persuasion across the landscape finds a curious parallel in a more hidden art, one that captures water not from floods, but from the cool, damp breath of the earth itself, within the dark confines of condensation tunnels. An explorer, lost in a dry valley for days, stumbles upon a crack in a hillside, a dark opening that exhales a cool, damp breath. He crawls inside, and in the profound darkness, his flashlight beam catches 1,000 tiny glints, droplets of water clinging to the stone walls and trickling down into a shallow, carved gutter. He has not found a spring, but something even more mysterious, a condensation tunnel, an underground river pulled directly from the air itself. Ancient cultures living in places like the Canary Islands and Cyprus mastered this hidden art, building these subterranean passages to harvest the one resource their arid coastal landscapes offered in abundance: nighttime humidity. They understood that the cool, stable temperature of the earth could wring moisture from the warm, saturated sea air. A modern tunnel engineer would point to the immense challenges these builders faced. Ventilation was critical, as stagnant air would quickly saturate and stop producing water, while structural integrity was a constant battle against collapse in the loose volcanic soils they often worked with. The construction process was a deliberate, multi-stage marvel. First, teams would dig a horizontal tunnel deep into a hillside, choosing a site carefully to intersect with the prevailing night winds that carried the humid air inland from the coast. The orientation was everything, a direct conduit for the invisible, moisture-laden breeze. Once the tunnel was excavated, the real engineering began. The walls and ceiling were lined with thermally massive rocks, dense stones like granite or basalt that possess a remarkable ability to stay cold. These rocks, cooled by the surrounding earth, would act as a giant condensation surface. As the warm, humid night air was drawn into the tunnel, it would contact these cold stones, and the water vapor would instantly condense, just like breath on a cold window pane. The final touch was a network of shallow gutters carved along the tunnel floor, designed to catch the countless tiny drips and channel them toward a central collection chamber or an underground cistern. Maintenance was a perpetual, dangerous task. Crews would have to regularly enter the tunnels to clear silt from the gutters and reinforce the walls against rockfalls, a testament to the value they placed on this self-filling water source. The Guanche people of Tenerife provide a stunning example of this technology's power. Living on a volcanic island with no permanent rivers, they relied on an extensive network of these condensation tunnels to capture the humid trade winds, providing a reliable source of freshwater that sustained their communities for centuries, entirely independent of rainfall. It makes you wonder, in our modern cities, what if the foundations of our buildings, our subways, and our parking garages were designed not just as empty space, but as active water harvesting architectures? This vision of turning our underground world into a hidden catchment system leads directly to another innovation, one that uses the earth itself as a living filter, the rock filter well. A well's water can gleam with a clarity that seems impossible in the dusty desert air. This purity was not a gift, but a deliberate creation, engineered through the simple, profound technology of the rock filter well. Ancient builders across India and the Middle East transformed ordinary wells into natural purification plants, using nothing more than the stones beneath their feet. They understood that the earth itself could be the finest filter, and they designed their wells to harness this power. Public health experts studying these ancient systems note a direct correlation, stating that communities using such multi-stage filtration saw a dramatic reduction in waterborne pathogens, a simple intervention that saved countless lives from dysentery and cholera long before modern medicine. The construction was a masterclass in layered design. First, a well was dug deep enough to reliably tap into the aquifer. But before the water was allowed to freely enter, engineers would construct a sophisticated filter at the bottom. They began by placing a thick layer of the largest stones, fist-sized rocks that created a stable base and trapped the biggest debris. Upon this, they added a middle layer of smaller, coarse gravel. The final and most critical layer was a deep bed of the finest material available, often clean, coarse sand or crushed quartzite. Water seeping into the well from the surrounding earth was forced to pass up through this graded sequence. The large stones stopped branches and leaves, the gravel caught smaller pebbles and silt, and the fine sand filtered out the microscopic particles and even some harmful bacteria, delivering remarkably clear water to the well's shaft. The life of such a filter was long, but not infinite. Over years, the sand and gravel would become clogged with the very impurities they removed. This required a system for maintenance. Builders often designed the well with a secondary access shaft or a wider mouth, allowing a team to periodically descend and carefully remove the old filter layers, replacing them with fresh, clean materials gathered from local riverbeds or quarries. This reliance on locally sourced stone and sand was key to the system's sustainability and widespread adoption. The stepwells of Rajasthan offer a breathtaking example of this technology's scale and social importance. These magnificent cavernous structures carved deep into the earth were not just sources of water but community centers and temples. At the heart of each stepwell, hidden beneath the water's surface, lay a massive rock filter bed. This natural purification system ensured that the water drawn by thousands of visitors daily was not just accessible but safe. It was a public health infrastructure built directly into the architecture, a low-cost, high-impact solution that served entire cities for centuries. This elegant method of achieving purity through the patient layering of stone makes you wonder, in a world still struggling to provide clean drinking water to all, what timeless principles are we overlooking in our pursuit of complex, expensive treatments? Yet, even the purest water is a fleeting resource if it cannot be protected from the desert's most relentless thief, the evaporating sun. A reservoir keeper in ancient Mesopotamia once faced a simple but devastating problem. His open-air storage basin, filled by the spring rains, was shrinking at an alarming rate under the relentless sun, threatening his community's survival. His solution was as elegant as it was effective. He gathered flat, lightweight slabs of local shale and slate and had them floated on the water's surface, creating a solid, mobile shield. Within days, the rapid drop in water levels slowed to a mere trickle of its former rate. This was the birth of the evaporation retardant layer, a technology of profound simplicity that turned waste into security. The principle is rooted in basic physics. Evaporation occurs when water molecules at the surface gain enough energy from the sun and wind to escape into the air. A floating rock cover fundamentally changes this equation. It acts as a physical barrier, blocking solar radiation from directly heating the water. Simultaneously, it drastically reduces the surface area exposed to the drying effect of wind, creating a still, humid microclimate between the water and the stone. An environmental scientist would note that such a layer can cut evaporative losses by 70% or more, a staggering figure in a world where every drop counts. The implementation of these covers was a precise craft. The first step was material selection. In Egypt, engineers used locally quarried sandstone slabs that were thin enough to float, yet durable enough to withstand years of immersion. In volcanic regions like Anatolia, they utilized pumice rafts, blocks of the porous, air-filled stone that are naturally buoyant. For larger, permanent reservoirs, builders did not rely on floating stones alone. They constructed fixed covers using a grid of wooden or stone beams suspended over the water, upon which they laid overlapping sheets of slate, like a roof over a hidden lake. This fixed design allowed for controlled access points where water could be drawn without disturbing the entire cover. The percentage of coverage was a critical calculation. Complete coverage was ideal for evaporation control, but builders had to balance this with practical needs. They left small, strategic gaps to allow for rainfall to enter and to prevent the water from becoming stagnant, ensuring the resource remained fresh and aerated. The impact on water temperature was another significant benefit. The rock layer acted as a thermal mass, absorbing the sun's heat during the day and releasing it slowly at night, which moderated the water's temperature and reduced the thermal stress that can also contribute to water loss. The historical reservoirs of the Hauran region in Syria stand as a stunning testament to this technology. Here, vast underground cisterns were supplemented with open-air reservoirs protected by extensive floating stone covers. These covers conserved enough water during the hot summer months to support not just the local population, but also the caravan trade routes that crisscrossed the desert, turning a way station into a center of commerce and stability. It forces a powerful question for our modern era, where massive reservoirs like Lake Mead lose colossal volumes of water each year to evaporation. What if we reconsidered these ancient, low-tech shields as a viable component of 21st century water management? This act of placing a simple lid over our most precious resource represents a final, logical step in containment, yet it hints at a more dynamic system, one that moves water upward against gravity itself through the silent, persistent pull of capillary action. A desert fig tree stands lush and green, its roots wrapped not in damp earth, but around a porous sandstone core buried deep below the surface. This stone is not merely a companion to the roots, it is a silent servant, a wick that tirelessly draws moisture upward from hidden reserves. This is the principle of capillary irrigation, a passive system where the physics of water itself does the work of watering. Ancient Andean farmers, along with their counterparts in the expanse of the Sahara, mastered this art of building underground sponges. They would fill planting holes with crushed sandstone or even broken fragments of unglazed pottery, materials riddled with microscopic channels. These tiny passages act like a bundle of straws, each one so narrow that the cohesive force of water molecules, a property known as capillary action, pulls the liquid upward against gravity itself. One botanist studying these ancient methods notes that this creates a continuous, low-level moisture supply directly to the root zone, mimicking the slow seep of a natural spring and encouraging deep, resilient root systems. The setup was a careful, layered process. Farmers first excavated a deep pit where a tree or a cluster of crops was to be planted. At the very bottom, they would place a reservoir of sorts, often a layer of gravel connecting to a hidden water channel that collected rare runoff. Upon this gravel, they piled their chosen porous material, the crushed sandstone or pottery sherds, creating a column that reached up toward the surface. The plant's roots were then nestled into this column. The entire system was covered with soil, shielding it from the evaporative sun. The choice of rock was critical. The porosity, the density of microscopic holes within the stone, determined its wicking power. A fine-grained sandstone with high quartz content was often preferred for its balance of durability and capillary efficiency. Not all crops thrived equally in this system. Deep-rooted perennials like fruit trees and drought-tolerant grains like millet were ideal candidates. Their root structures perfectly adapted to draw from this steady, subsurface source rather than relying on surface dampness. A remarkable example of this ingenuity persists in the Wadi Rum of Jordan. Here, nomadic communities created hidden gardens in the desert's heart. They would bury porous limestone rocks beneath their date palms, connecting these subterranean wicks to shallow, hand-dug wells. The rocks would slowly pull moisture from the well's damp walls, delivering it directly to the thirsty roots and allowing the trees to flourish on a fraction of the water required by surface irrigation. It compels a modern question as we face growing water scarcity in agriculture. What if our fields were underpinned by such simple, self-watering stone networks? This elegant, gravity-defying pull of water through stone represents one of the most subtle forms of ancient irrigation. Yet, other engineers sought to move water on a much grander scale, not with a slow wick, but with the powerful, rhythmic pulse of a pump driven by the water's own force. A mountain stream tumbles down a rocky slope, its constant flow a force that seems to go to waste. Yet, forgotten engineers found a way to make this very stream lift its own water to a village perched high on the cliff above, using a device that required no fuel and had no moving parts in the traditional sense. This was the hydraulic ram pump, a masterpiece of energy recycling carved from the landscape itself. Ancient Chinese and Greek inventors developed these systems, often crafting the critical pressure chambers and valve seats from durable stone to withstand a lifetime of powerful water hammer. The principle is a clever manipulation of physics. When flowing water in a pipe is suddenly stopped, its energy does not simply vanish. It converts into a sharp spike in pressure. The ram pump harnesses this shock wave. A mechanical engineer specializing in fluid dynamics would explain that the efficiency comes from this direct transfer of momentum, a process that can lift a small fraction of the incoming water to a height many times greater than the original fall, making it perfect for remote, mountainous regions. The construction was a precise, multi-stage process. It began with the drive pipe, a long, rock-lined channel or a hollowed-out log that carried water from the stream down a steep grade. This gradient was essential as the water needed to gain enough speed to create the necessary force. At the bottom of this pipe stood the valve house, a small, robust structure built from stone. Inside, a heavy valve, often a carved stone plug or a weighted lever, was carefully balanced. The flowing water would initially push this valve open, but as the speed increased, the force would suddenly slam it shut. The instant stoppage created a powerful pressure surge, a water hammer that forced a pulse of water past a second, one-way valve and into a sealed air chamber, also carved from rock. This chamber, with a pocket of trapped air acting as a spring, smoothed the violent pulse into a steady stream that was then pushed up the delivery pipe to the village reservoir high above. Tuning the system was an art. Builders adjusted the weight of the waste valve or the length of the drive pipe to match the stream's specific flow rate, ensuring a consistent rhythm of opening and closing that could run for years unattended. Maintenance was straightforward, focused on the stone components. The valve seats would occasionally need to be smoothed to ensure a tight seal. and the air chamber might need to be recharged if the air dissolved into the water over time. The scalability of these pumps was one of their greatest strengths. A small ram could supply a single household, while a large one with a massive stone chamber and a wide drive pipe could irrigate entire terraced fields. We see this beautifully illustrated in the ancient Tibetan monasteries that cling to the Himalayas. Here, monks used hydraulic ram pumps, built with local slate and granite, to lift water from raging glacial streams to their sanctuaries high on the mountainsides. This provided a reliable supply for drinking, gardens, and ceremonial fountains, all powered by the eternal flow of the meltwater itself. It was a perfect symbiosis with a powerful environment. This brilliant act of coaxing water to lift itself using only its own inherent energy represents a pinnacle of passive engineering. Yet, once that water was delivered, whether by ram pump or gentle canal, another challenge awaited, one of clarity and calm, managed by the quiet, patient work of the Sedimentation Weir. A river can clean itself given the right invitation. This is the quiet genius of the Sedimentation Weir, a simple barrier of stone placed not to dam the flow but to slow its heartbeat. In the ancient canal systems of the Indus Valley and North Africa, these weirs were the unsung heroes of longevity, a low-tech solution to the relentless problem of silt. When fast-moving water laden with sediment hits a low wall of strategically placed rocks, its speed drops instantly. The heaviest particles of sand and clay, no longer suspended by the current, simply settle to the bottom, leaving clearer water to spill over the weir and continue its journey. One modern water manager working with traditional systems notes that this single intervention dramatically reduces canal siltation downstream. By preventing the buildup of sediment in the main channels and reservoirs, the entire system's functional life is extended for generations, he explains, a lesson in preventative care we are still relearning today. The construction of these weirs was a study in practical geometry. Engineers did not build them as solid walls, but as porous, rock-filled structures. They selected locally quarried stones of various sizes, stacking them in a loose, interlocking pattern that could withstand the water's pressure without mortar. This local sourcing meant repairs were fast and easy, as replacement stones were always close at hand. The placement was calculated with precision. Weirs were installed at regular intervals along a canal, each one catching a little more of the suspended load. The angle of the weir relative to the flow was critical. A perpendicular wall created the most abrupt stop, ideal for catching the coarsest gravel and sand. A slightly angled weir, however, would create a gentler, spiraling current that could sort finer silts, guiding them toward deposition zones at the channel's edges. But the stone alone was not the whole system. Ancient builders often combined these rock structures with living buffers. They planted dense, deep-rooted vegetation along the banks just upstream of a weir. The plant roots held the soil firmly, reducing the amount of new silt entering the water in the first place, while the above-ground stems further slowed the current, enhancing the weir's settling power. This integration of biology and geology created a self-reinforcing cycle of clarity. The maintenance rhythm was built into the design. The rocks in the weir were deliberately removable. After a major storm or at the end of a rainy season, community members would work together to temporarily disassemble sections, scooping out the accumulated sediment and piling it on the banks. This silt was not waste, it was nutrient-rich soil that was then used to fertilize nearby fields, closing the loop in a perfect example of sustainable resource cycling. The scale of this ambition is best understood in ancient Mesopotamia, where vast irrigation networks fed the Fertile Crescent. Here, sedimentation weirs were a cornerstone of hydraulic management. quietly ensuring that the canals which watered the cradle of civilization remained free-flowing for thousands of years. They understood that managing the water meant managing the dirt it carried. It makes you reflect on our own concrete-lined flood channels, where sediment builds up until expensive dredging is required. What if we redesigned our waterways to clean themselves, just as these ancient systems did? This elegant approach to managing clarity and flow finds a parallel in another subtle art, one that uses stone not in the water, but on the land to guard against the thirst of the sun. A farmer in New Mexico watched his bean plants wilt under a brutal sun, their leaves curling into crisp brown fists. Then he remembered stories from his grandfather, tales of a gray blanket that protected the earth. He spent weeks gathering truckloads of smooth gray river stones, spreading them in a thick layer across his field. That season, while his neighbors' crops failed, his yield doubled. The stones had not brought more rain, but they had made every drop count. This was the power of rock mulch, a living skin for the soil perfected by indigenous cultures across the globe. From the Hopi farmers of Arizona to the terrace builders of the Andes, these ancient agriculturists understood that the right stones could create a protective microclimate, a stable environment where fragile roots could thrive. They selected their materials with care, choosing river pebbles for their smooth, interlocking qualities or porous lava rock for its excellent insulation. Horticulturists studying these systems note the multi-layered benefits. The rock cover acts as a physical barrier, drastically reducing the wind and sun that steal moisture through evaporation. It also suppresses competing weeds, which would otherwise rob the soil of its precious water. Perhaps most importantly, the stones regulate soil temperature, absorbing the sun's heat during the day and slowly releasing it through the cool desert night, protecting roots from extreme swings that can stunt growth. Applying this stone blanket was a deliberate process. Farmers first cleared and leveled the soil, then laid down a layer of rocks several inches thick. The thickness was critical. Too thin and weeds would push through, too dense and it could prevent water from seeping down. They left strategic gaps in this stony armor, creating perfect pockets for planting seeds or young seedlings. The color of the rocks was not an afterthought. Light-colored stones like white quartz or pale limestone reflect sunlight, keeping the soil cooler in intensely hot climates. Darker rocks such as basalt absorb more heat, which can be beneficial in cooler high-altitude gardens to extend the growing season. These mulches were often integrated with other water-saving methods. In some ancient fields, the rock layer was placed over a shallow network of buried clay pots or channels that delivered water directly to the root zone, a precursor to modern drip irrigation that minimized any loss to the surface. The Anasazi people of the American Southwest left a stunning legacy of this practice. In the arid mesas of Choco Canyon, they cultivated vast fields of corn, beans, and squash. Archaeologists have found extensive areas covered with a dark pebble mulch, a technology that conserved soil moisture, reduced erosion from rare but violent downpours, and allowed this sophisticated civilization to flourish for centuries in a landscape that challenges modern farmers. It forces a powerful question about our own agricultural habits. In a world of resource-intensive farming, what could we regain by learning to work with such simple, permanent ground covers? This ancient wisdom of protecting the soil from above finds its ultimate companion in a final, elegant form of harvest, one that gathers water not from the ground, but from the very way it moves through the air. A spiral of glistening stones catches the first light of dawn, each dark surface beaded with 1,000 tiny droplets. This is not a random pattern. It is a spiral rock collector, a perfect fusion of sacred geometry and hydrological genius, designed to turn the entire surface of a rock into a water-harvesting canvas. Ancient Celtic builders and desert cultures from North Africa to the American Southwest saw the spiral not just as a symbol, but as a functional tool. They carved or arranged these winding pathways into rock faces, transforming them into efficient systems for gathering every possible drop of condensation and runoff. At sites like Newgrange in Ireland, the famous spiral carvings adorning the entrance stone are often interpreted as celestial symbols, yet some anthropologists propose a more grounded, yet equally profound purpose. The spiral represents the journey of water from the sky to the earth and into the body, one expert notes, suggesting that these carvings on sloped stones may have literally channeled rainwater or morning dew into ceremonial basins, making the ritual site a self-sustaining source of both physical and spiritual nourishment. The design of these collectors was a masterclass in passive guidance. Engineers would first identify a large, sloped rock surface with a naturally impermeable quality, like granite or dense slate. Using stone tools, they would carve a shallow, continuous groove in a spiral pattern, winding from the outer edges of the rock inward towards a central point. The genius was in the groove's profile. It was not a deep trench, but a gently rounded channel, just deep enough to guide water but shallow enough to allow capillary action to pull moisture from the damp rock surface into the flow. The entire spiral acted like a catchment net. When dew formed on the cool stone at night or a light rain fell, the water would naturally follow the path of least resistance, trickling along the carved spiral. The centrifugal force of the winding path helped to keep the water moving, preventing it from stalling and evaporating, guiding it inexorably toward the center. There, a small, drilled hole would allow the collected water to drip through into a waiting underground storage jar or a sealed ritual pit. The scale of these spirals was directly tied to their purpose. A small, intricate spiral carved near a solitary dwelling might gather just enough pure morning dew for a daily drink. A massive spiral pathway, built from arranged stones across a hillside, could channel significant runoff from a light rain into a communal cistern. The alignment was often deliberate, with the entrance or focal point of the spiral oriented toward the rising sun or specific stars. This was more than ceremony, it was practical astronomy. The position of celestial bodies helped mark the seasons of heaviest dew or the arrival of rains, ensuring the community knew when their spiral collectors would be most productive. This seamless blending of the cosmic and the practical challenges our modern separation of disciplines. It makes you wonder, in our search for pure efficiency, what profound connections between our infrastructure and our humanity have we lost? Desert rock was never a barrier to these master engineers. It was their greatest ally. From the deep, cool darkness of the Qanat to the skyward reaching fog nets, they saw potential where we might only see desolation. They carved the living stone into cisterns that drank the rain and shaped it into channels that commanded gravity itself. They learned to pull purity from poison using solar heat and to coax moisture from empty air with nothing but a pile of dark, dense rocks. Their toolkit was the landscape itself, their power source the sun, the wind, and the unyielding force of gravity. These were not miracles, but a profound demonstration of human adaptability, a deep collaboration with the natural world that turned the most extreme environments into sustainable homes. This legacy of ingenuity is not locked in the past. As climate change tightens its grip and water scarcity becomes a daily reality for millions, these ancient techniques whisper a vital secret. The solutions to our most pressing crises may not require complex technology, but a return to a simpler, more profound wisdom. The principles of harvesting rain, recharging aquifers, and designing with nature are more relevant than ever. You can explore this history firsthand at places like Petra or the ancient stepwells of India, or even begin on a smaller scale. Try building a simple rock mulch in your own garden to conserve water, or set up a basic solar still. The journey to rediscover these skills starts with a single step. Our channel is dedicated to unearthing more of these forgotten mysteries of human ingenuity. If this exploration of how to pull water from stone captivated you, subscribe for more journeys into the past that can illuminate our future. Let us know in the comments which of these ancient techniques amazed you the most. This journey through time reminds us that the keys to our survival have often been hidden in plain sight, waiting for us